All right, question 4 of the 2017 A-level physics paper from AQA. So here we've got an engineer who wants to use solar cells to provide energy for a filament lamp in a road sign. So first thing he wants to do is find out the EMF and internal resistance of a solar cell under typical operating conditions. So what we have here is a potential versus current graph, and from this graph he's deduced that it has an EMF of 0.7 volts and an internal resistance of 8 ohms. Explain how the engineer uses the solar cell to obtain the values for this here. So you don't have to actually obtain the values yourself, you have to explain how it uses it. So, very straightforward. Your EMF, it's the y-intercept of the line of best fit. Okay, so your y-intercept, that's your EMF. Internal resistance is the negative of the gradient. Okay, just paying attention to units though, but that's how you would find these values from this graph. So, moving on. So to operate efficiently, the lamp on the roadside needs a minimum current of 75 milliamps. At this current, the resistance of the filament lamp is 6 ohms. So we've got two possible circuits. Deduce using calculations whether the circuits are suitable for this application. So we know that our internal resistance is 8 ohms. So each one of these is 8 ohms, 8 ohms, 8 ohms, 8 ohms. Now, for this circuit here, we have an EMF that is double because EMFs in parallel don't add together. So EMF here is 1.4 volts and the EMF here is 0.7 volts. So our current is going to be equal to the voltage divided by resistance plus the internal resistance. So for circuit 1, well, might as well look at what my resistance here is. So this resistance, so these two in parallel, is actually equal to 4 ohms. So my total internal resistance is 12 ohms. Okay, so the parallel section is 4. Added together with the series section makes 12 ohms. Here it's 8 ohms for the internal resistance. Not really good that the internal resistance is higher than the resistance of our cell. It means we're actually dissipating more energy in the power supply than we are in the lamp, but that's beside the point. This is what we've been given. So circuit 1, I is 0.7 divided by 8 plus 6, and that's 50 milliohms, I believe. Yeah, 0.05 amps, or I said ohms, which is 50 milliamps. That's not suitable. Okay, circuit 2. I is equal to 1.4 divided by 12 plus 6. 6 plus 12 is 18. Oops. Is 77, so 0.078 amps is 78 milliamps. That checks out. So circuit 2 is suitable. Okay, so circuit 2 does work. So if you don't have the value judgments, you won't get full marks because it says deduce, okay, whether they are suitable. Okay, so you have to have those value statements in there. You can't just throw numbers out there and say, like, the rest is an exercise for the reader. This isn't a maths textbook. So, last part of it, solar cells convert solar energy to useful electrical energy in the road sign with an efficiency of 4%. The solar cell supplied by the engineer has a total surface area of 32 centimeters. Calculate the minimum intensity in watts per meter squared of the sunlight needed to provide the minimum current of 75 milliamps when the resistance is 6 ohms. So, okay, so the power that we need is I squared R, so 0.075 squared times 6.0 0.075 squared times 6. So the power is 33.75 milliwatts. Okay. The total power that we need then, because it's converting at an efficiency of 4%, is so P divided by PT is equal to 0.04. So PT is power divided by 0.04. Okay, divided by 0.04 is, I need 0.84375 watts. Okay, and the area it's hitting is 32 centimeters squared, but to go from centimeters squared to meters squared, I have to divide by 10,000. Yeah, 100 squared. So, the intensity should be 0.84375 divided by 32 times 10 to the minus 5. Okay, divided by 32 oops. It's 5. Okay, that's actually, okay, so it says I need 2,600 watts per 2.6 times 10 to the 3 watts per meter squared, which is probably about right, except that that's quite a bit higher than like noontime. Am I off by power of 10? Why am I off by power of 10? Because it's not 10 to the minus 5, it's 10 to the minus 4. Okay. Watch your figures. Right, because yeah, it's divide by 100, divide by 100. That's obviously to the 4. That's okay. So you can see I was already saying like okay, 2.2600 watts per meter squared is more than well, it's about 80% more than actually no, it's more than double like noontime at the equator solar radiance. So yeah, this is much more reasonable. 260 watts per meter squared. Okay, so just watch your powers of 10 there. Don't make mistakes like I did. All right, that's question 4.